Hi everyone, good afternoon. So it is a great pleasure to introduce you to Professor Raúl Angulo. One of the few things I'm most proud of in my professional career is to be responsible for bringing Raúl and his wife Silvia here to Spain. Raúl has been in Spain since 2012, I think, or 2013, yeah, so almost 9 years, about 9 years or so. So he's professor now at the IPC, and today he's going to be talking about simulation, the formation of a structure in the universe. So, I'll give you a warning when it's 5 minutes to the end of your talk. Is that okay? Okay.
Yeah, thank you. So I'm very happy to be here. So to see so many young people, I never thought I was going to say that myself, but so yes, I think you have been listening about various topics in cosmology, about how different dark matter candidates, the physics of the CMB, and about the large-scale structure. So in this lecture, I will try to introduce you a bit to the world of numerical simulations and how we perform the calculations such as the one that is shown here, this distribution of dark matter as predicted by a numerical simulation. And this is a relatively large topic, so I will just try to give you a general overview. I will just highlight several places where research is being carried out, nowadays. And then I will be happy to talk to you more about any of these things. So the main motivation for the, cosmological large-scale structure simulations is to explain the universe that is around us, right? When we put our telescopes and map the universe, we see pictures like this one, where we see the tons of different galaxies, different colors, sizes. We see them arranged in this filamentary structure. This is as measured by Sloan, the CSS survey. And they form all this filamentary pattern. And the question is, can we explain why the universe is like this? Right? Why it does not have a different, these filaments, why don't they have a different shape, right? Do we need a different type of physics? And is our understanding of the universe good enough to explain this in a qualitative and quantitative manner? So this is in principle a relatively easy problem in physics, in the sense that it's a well-posed problem. Right? We know what the starting situation of the universe for this nonlinear structure to form is, and this is given by the CMB. I believe you have lectures about it. So we have a kind of a picture of what the starting point of the universe should be like. And then we know the laws of physics, gravity, hydrodynamics, how stars form, and so on. So we need to you need to evolve this initial field into the present day, right? We need to account for gravity and baryonic physics and so on. The problem is that this is a not so straightforward problem to solve, because even though in the CMB the physics is linear, we can do perturbation theory and solve this very accurately. Gravity makes things quite messy, right? Things, the density fields become very quickly nonlinear, non-Gaussian. There are non-local processes, so it becomes very, very difficult to solve analytically this initial condition problem. And of course, then we have also all the uncertainty about galaxy formation physics and gas physics, and all the complicated astrophysics is going to be at play. So we cannot solve, we don't have really a theory to solve how to go from this to the velocity, to the galaxies. So we need to resort to numerical experiments, right? This is so this is quite, it's akin to several other areas of physics, where we just take our problem. We started with initial conditions. We put in our supercomputers what the laws of physics are, and then we solve them numerically, and to end up with a result like this, right? So this is quite useful because it allows us to play with the universe, right? We could see how the universe would look like if we had a different law of gravity, right? If dark energy was not a cosmological constant, but was a dynamical field. If we had an additional fifth force, right? Anything we want, we can code up in our simulations, and then make prediction for the nonlinear universe and compare it against the observed universe, right? And then we try to infer back what is the fundamental properties of the universe, right? And this is roughly how the research in the field of numerical simulations, large-scale structure numerical simulations, is conducted. So also in this way, we were able to demonstrate that, that the standard cosmological model and the CDM is actually a reasonably good description of many nonlinear observables, right? So, so the final picture is something I'm going to show you here. It's a movie done by the Eagles collaboration. This is a state-of-the-art hydrodynamic simulation where you try to solve both the expansion of the universe, gravity, and galaxy formation physics. So we see that the initial very small fluctuations start growing, and then they collapse. They form smaller clumps, larger clumps that they merge and form larger and larger structures. Then inside those structures, now we can see the gas in this case. The redder is denser gas. And we see that the gas starts to be collected. It starts actually cooling, loses energy, and then settles in something like a disk. And now we switch to stars, and then we see that they form a nice plane like those that we observe. Now we reach roughly redshift 1. The galaxies keep growing. Now you will see mergers, other structures that are being accreted. They contribute to, with more gas, and the galaxy keeps growing and becoming bigger and bigger. So this is kind of a grand design spiral galaxy at redshift 0. So of course we do this not only for a single galaxy, but for thousands of them. Now we are zooming out. We see that the galaxy was in the center of what we call a dark matter halo, and then there's all this filamentary network of halos of different sizes and properties. So this is the standard picture that has emerged after many years of development and different fronts. We can also do a more quantitative comparison. You might have seen this picture that shows the filamentary structure as measured in actually this is the 2DF survey. No, sorry, the Sloan survey. And in the bottom part is the same region or the same volume, but predicted by a numerical simulation. So we see a very good agreement, a quantitative agreement that so we're able to explain, thanks to numerical simulations, all the nonlinear structure in the universe. We can also compare, in this case, the average dark matter around galaxies of different sizes. And it's also a superb agreement between what numerical simulations predict and what we observe in the real universe. So so this is, as I was telling you, this is the result of many years of development, progress from thousands of different scientists. And nowadays, these type of simulations are a very useful tool in many different areas of cosmology. As I was telling you, you can create virtual galaxy populations that you can test your analysis pipeline where you could come up with a new idea of measuring something about the universe. You can test it in your simulations first, see whether it actually recovers the correct quantities that you want to measure. You can use them to develop better analytic treatments of large-scale structure. Maybe you come up with an idea of how to do better perturbation theory, and then you can compare against numerical results. You can test what happens, for instance, if neutrinos had a 0.1 eV of mass, right? How the observables would be different, and you can do with you come up with a new theory of dark matter interaction, so on. You can carry out numerical simulation to test the observability of such thing. You can also understand your observational errors. You can try many different universes and then quantify what is expected uncertainty in a given measurement, the power spectrum or any other statistic. And potentially we will be able to constrain the underlying physics, cosmological parameters directly with simulations. So, okay, so the structure of my talk, I will try to, I was trying to give you a bit of motivation why these numerical simulations are so useful. And I will try to now explain to you the basics and give you an overview of how these simulations are being carried out and what are the main ideas behind them. So essentially, I have 4 different topics. The first one would be basic methods and algorithms. Then I will show you a couple of examples where we have varied the fundamental assumptions about numerical simulations. Then I will recount the state of the art, and I will give you some thoughts for the future. So I was telling you this is a large field, and I will just very briefly touch on many things. So if you are interested in something more in depth, this is a review I wrote with Oliver Hahn last year. This is open access. It's in the archive, where we go really into much more detail in everything I'm going to talk about, and way also and many other things. Yeah, so if you're interested in knowing more the details, I will recommend you. That would be a good resource, I hope. Okay, so so the basic methods and algorithms. So I will now focus on the simplest possible case that we can simulate, right? So that is the case of a cold collisionless fluid under the effect of self-gravity in an expanding universe. So what does that mean? So so we are going to assume that all the matter in the universe is made out of collisionless, of essentially dark matter, or that is justified because of different observations tell us that dark matter is the dominant gravitating component in the universe, right? It's 5 times more abundant than normal atoms and baryons. So that that is what it means, the gravity part. Then we are going to assume that dark matter is cold, which means that the microphysical velocity of dark matter is much smaller than the motion that it has inside dark matter halos in the cosmic web. Also, that this seems to be supported by essentially every observation that is sensitive to this, from the Lyman alpha 4s, abundance of Milky Way satellites, or so. I'm sure you have heard about them. Collisionless means that dark matter is non-interacting. Means there is the cross-section with itself or with other components of the universe is 0, and I guess there is this seems to be the case from observations of gamma rays or mergers of clusters. We are also going to assume that the law of gravity is given by general relativity. Also, all tests of GR have been or GR has passed every single test that has been subjected to. And the final one is that we are going to work in the Newtonian limit of GR, which means that we first linearize the Einstein's equation, keeping only linear terms of the potential, and then we focus on sub-horizon scales. So essentially means that potentials travel infinitely fast. And we are going to assume the no-back reaction, which means that the metric of the overall universe is the same as the metric of the average of the matter distribution. Okay, so this is the simplest case. It's what we call a dark matter simulation. And under these assumptions, the underlying equation that governs the evolution of dark matter is the Vlasov-Poisson. This is written here, and what it tells you is that there is you can imagine there is the full dark matter in the universe is given by its distribution function f, that just tells you the density of matter in a given volume in phase space, velocity, position. Right, so this Vlasov-Poisson tells you that this phase space is conserved along the trajectories of the evolution of this dark matter. And that is there is an external potential, like a force field, that is given by, in this case, the Poisson's equation. That is density is given by integral of the phase space distribution over velocity space. Means that it's a self-gravitating fluid. Okay, so the fact that dark matter is cold means that this distribution function is you can imagine is in a space. There's only one possible velocity in every location in the universe, right? So at every position x, there's only one possible velocity, right? So that in 1D, let's imagine how that would be. So you have velocity, position. Dark matter would just be a line here, right? So there's only one possible velocity at a given position x, right? So now this distribution function will evolve. This distribution function can actually wrap into itself, could actually do crazy things. What it cannot do is that it never can tear nor intersect. But it can actually fold, and these are regions where what we call shell crossing that you might have heard in previous talks. Okay, so this is in 1D. In 2D, now you can imagine that dark matter, it forms like a sheet. So this is velocity to positions, and now the distribution function of dark matter occupies like a submanifold in this six, or in this case, 2+1 space. Okay, so now we can see how the evolution is in 2D. So now it's this is the dark matter density, and now evolving under self-gravity. So now we see that these regions, for instance, this filament, start to become denser and denser. It's under its own gravity. So in this region is where this dark matter sheet is folding into itself. You can see these sharp transitions, which correspond to these caustics. This is regions where the dark matter goes there and comes back. And then that's how the cosmic web appears. Okay, so now this is the basic equation that we need to solve. So how do we do it, right? So in the most commonly adopted method, which is the n-body discretization, what we say, okay, let's take this distribution function, and we don't know how to solve in full generality the Vlasov-Poisson. What we can do is to sample it with simulation, what we call simulation particles, right? So you can imagine that there is a position velocity, you have your distribution function, and now we represent a full volume in phase space with one simulation particle, and then we do that for everywhere in the space, right? And then when we do that, actually the Vlasov-Poisson becomes, essentially the Hamiltonian of classical mechanics, right? It's a usual kind of, equation that you will have evolving a set of n particles. Okay, but this is not the only way that we could do the discretization. It's a most common one, but it's not the only one. This is the n-body. Okay, unfortunately, it doesn't look very well. Okay, so there should have been here a line with the phase space. We can, right, so each particle was described by a position and a velocity, right, momentum. But we can also solve or promote them to actually tensors, and this is called the geodesic deviation equation. So where we solve not only for the position and velocity of each particle, but also what we call the distortion tensor, which is how the position and velocity at that location is stretched or is evolving. Right? So that will tell us something more about how the space is, the dark matter distribution is changing. Another way of doing the discretization is through phase-space tessellations. So instead of assuming that essentially you have particles, we just join them with a given volume element, right? That is determined by this kind of vertices, but that tends to reconstruct the full phase-space distribution. That's another method that only now has become possible. And finally, we try to do the full phase-space solution to the Vlasov-Poisson, which we discretize the full velocity position space into kind of voxels, no? And we try to solve the Vlasov-Poisson in this way. This can be done, but the problem is it's super, super expensive and has been done only in a handful of cases. And actually, there are some technical problems why this tend to not be so good. This has become possible under certain circumstances, and nowadays has been shown to kind of agree with n-body, but also tends to be way more expensive. And also this has much more information, but it tends to be also computationally much more expensive than typical n-body. So, in practice, n-body is the discretization choice for most of works in the field. Okay, so what we need to do now is then to solve for the n-body equation. This is the standard equation. That is that the acceleration is 1 over distance squared, sum over all particles in your system. And this is the same equation that governs the motion of planets, globular clusters, and all the way down to the large-scale structure of the universe. Okay, so the way we solve this is relatively simple. We just first we need to solve this as a function of time. So we do typically a second-order leapfrog integrator of this. These are the equations. That essentially means that we take a position, a distribution of particles. We estimate accelerations. We advect velocities And then with that velocity, we then advance particles, compute forces again, and update velocities, and so on. Right? So this is has some nice properties of time reversibility and so on. Another very important thing is that even though it's a first order method, the errors tend to go like delta t cubed. So the errors tend to be like a second order method, even though it's a third order accurate method, but it's only first order. When you have the simulations, you can do you have to do this also many times, and the choice of the time scale has to be very different in different regions. Inside halos, the dynamical timescales tend to be very short. You need to choose very small timescales. In voids, for instance, timescales particles move more or less in a straight line, so the timescales, the time steps can be longer. So we tend to have adaptive methods for computational efficiency. And one part that is actually been quite active nowadays is how to improve upon this type of time integrator so that it converges faster than a simple formulation, right? And there are some ideas called COLA, FastPM, and although they're not rigorously correct, they tend to be quite useful for research in certain situations. Okay, so now the next problem is that now we have this group of particles. We need to, we know how to advance them. We need to now compute the accelerations. In principle, you can just sum over every other particle in your system, but the problem is that this is a very expensive. It scales like the number of particles squared. So there are a lot of different methods to speed these things up. The two most famous ones, one is the particle mesh. So essentially take your particle distribution, write your Poisson's equation, and try to solve this equation directly in Fourier space. Another idea is to, instead of partitioning your space into cells, you can do what's called hierarchical trees, which you group particles and then describe, for instance, all these 10 particles by its center of mass, for instance. And then when you want to compute the force that they exert on this particle, instead of summing over this 10, you just consider here like a macro particle. Right, and these are the most basic algorithms. You can go very, way more complicated than this, and combinations and different. You have also many different alternatives. Okay, so one of the problems of this equation, even though it's kind of quite simple, you might notice that when two particles get arbitrarily close to each other, this 1 over distance cubed explodes. So this diverges. So what we do is we introduce a softening length parameter, this epsilon, that regularizes these close encounters. This is what determines the resolution of a simulation, essentially. So then another area of research is how to choose this parameter optimally so that you get the most out of your computational resources. And there are different arguments. For instance, you would like that the acceleration induced by this, or the maximum acceleration that two particles can have, is never larger than the mean acceleration of particles in a halo. Another criteria that you might choose is that the two-body relaxation timescale inside your system always to be much longer than the typical dynamical timescales in your objects. And again, there is like a lot of different research trying to find what's the optimal one. Okay, so now we know more or less how to run our simulations, and we have to choose how to initialize them. And there are like different possibilities here, and these are different type of simulations. One of them is that you say, okay, I want to simulate a random region of the universe. This is so you can just create a Gaussian random field that's consistent with the CMB and initialize your particle distribution like that. Or you can focus all your computational resources into a single object. That's called a zoom-in simulation, and that's useful to simulate, for instance, the Milky Way halo. These are, as I was telling you, could be just a random realization of the universe, but you can also create a realization that is consistent with what we observe. And I believe Francisco Quitaura talked to you about these constrained realizations. So you can use them as initial conditions for simulations. Or you can use what's called separate universe, in which you take a simulation and then you by hand increase the background density so that it mimics what would happen with the structure if it formed in a large overdensity or in an underdensity. And in this way, you can do control experiments to understand the role of primordial non-Gaussianity or differences with isocurvature modes and so on. Okay. Yeah. Okay. So roughly, this is how schematically how an body simulation would work. You choose your discretization of space. You compute your initial conditions, the type of simulation you want to run, and then you loop over n time steps where you compute in every time step the forces that particles feel with against each other, and then you advance the system until you arrive at a given time. And this is what is shown here. These are your simulation particles, and then underline is how they reproduce the underlying dark matter field. Okay, so this is now the power spectrum as a function of scale, and in solid lines is the prediction from linear perturbation theory, and we can see, and in symbols is the prediction from our n-body code. You can see on large scales they agree. So perturbation theory reproduces correctly the distribution of matter in the universe, but as we go to smaller scales and late times, we see that the numerical results, for instance, here these gray symbols, differ significantly from the linear theory predictions, right? So this is an example of the usefulness of numerical simulations, right? Identifies regions where your analytic might or might not work. You might also see some weird features here on a small scale, right? So this is a very early times, this orange, and then you see that agrees with linear theory and then kind of increases very rapidly, right? So this is actually numerical artifacts. Right? It's also another very important thing in the field of narco structures, that we are solving numerically a problem, so we should not trust them that they're just perfect because of that. But there are a lot of numerical choices that you need to be aware of, and that the quality of your predictions depends a lot on about those numerical choices. And here I list 4 of them, where there's a lot of research going on in the field to guarantee that the robustness and the accuracy of your results. So, for instance, numerical errors nowadays there are several comparisons in the literature with different codes, different groups around the world, and then they all tend to now agree to roughly sub% level down to kiloparsec scales. Another issue that you need to be aware of is how to set up the initial conditions and how do they transition. How do you start your simulation? And again, there's a lot of research in this area, and then I think the outcome nowadays is that you would like to use a higher order version of perturbation theory to initialize the position and velocities of your particles and to start as late as possible. In this way, you minimize also other discreteness errors. There is also issues with the size of your simulation. You need to be able to, you would like to run simulations that are large so that you capture all the possible couplings between small and large scales. And of course, the mass resolution, you also need to be able to resolve all the small scales and small halos. And again, you have to be aware that all these might affect the results. But I think as a field, I think we have reached, after a lot of work, we have reached a consensus of understanding very well all these, the sources of these numerical issues. Okay, so I try to give you a hint of an overview of what these numerical simulations do, the underlying assumptions, and so on, for this simple case called collisionless, dark matter only, Gaussian, GR, and with classical particles. But each of these assumptions can be broken. You can investigate what would happen if instead of cold dark matter, you have a warm dark matter, right? You can try to search for different, or you can simulate cases where there is self-interaction in dark matter. Instead of considering only dark matter, you can add baryons or neutrinos or multiple fluids. You can not consider Gaussian initial conditions, but you can also simulate initial fields where there is a primordial non-Gaussianity, which might be a signature of essentially inflation. You can also simulate departures of GR, and instead of assuming classical particles, you can simulate primordial black holes or axions, or even assume that the dark matter has quantum properties, even on galactic scales. It's called wave or fuzzy dark matter. Okay, so the first case I wanted to mention to you is the case of neutralino dark matter, right? So if we think that the dark matter is made of a particle, cannot be completely collisionless, right? Needs to have at least some non-zero interactions to be able to be produced at the first place. So you have many different candidates, and one of the most popular one are neutralinos of about 100 GeV. This is some particles predicted in supersymmetry. So, and what that means is that they will have some primordial velocity in the early universe, and when you have small fluctuations in as a result of inflation, you have an overdensity, and because of this particle velocity, if you have an overdensity, dark matter will escape from it. The typical length that particle travels is called the free streaming. And then you can imagine that you have fluctuations smaller than that free streaming scale. Those will be erased, right? You will not be able to see anything below that free streaming scale. And that is what determines the minimum scale that collapses in different dark matter scenarios. For this 100 GeV scale, that corresponds to about an Earth mass. So one line of also research in these numerical simulations is try to go and simulate this very first Earth mass structures. And in principle, that would require roughly 10 to the 21 orders of magnitude in scale. But that was recently achieved in this VVV project, where they took a region of the universe, they focus on voids, and they zoom in, and then they focus again on voids of that zooming region, and so on. They did it hierarchically, and they managed to arrive to this Earth mass scale. So this you can also focus on small regions of the universe to be able to reach the mass resolution necessary to resolve this structure. And this is a movie about the formation of an Earth mass halo at redshift 300. So you can see that how this initially homogeneous field collapses and then forms a much larger halo, and then you see all these little clumps are the remnants of the other halos that fell in, and they tend to orbit. And now we expect the Milky Way to have a huge amount of these objects, which might actually be detectable through gamma rays. Okay, so we can also assume that dark matter is something warmer, that the velocity dispersion is even larger, right? And that's what we will call warm dark matter. And the same physics happens, but it's just on different scales, right? There is this is the power spectrum as a function of scale, and there is some suppression on the small scales, where this scale depends on the typical velocity of this dark matter particle. And yeah, and there is a lot of research about try to put constraints from observations on the mass of this dark matter particle, right? So we take numerical simulations. We say, well, if we think dark matter is a 5 keV particle, we expect now this power spectrum, so no structures below this scale, right? And we can go and search whether that's the case or not. Okay. Okay. So some signatures of this is the, if we look at a halo like the Milky Way, we see a lack of small-scale structure, and also the concentration, or these halos tend to be less concentrated when you have this warm dark matter. And this could be another signature. We can also, as I was telling you, dark matter needs to be self-interacting to some degree. That could generate, for instance, gamma rays or other byproducts that could be searched by CTA in the future, other gamma ray telescopes. Could also decay in other particles, and there are like searches in all these directions. Another one could be that if it interacts with itself. Now, in this case, we have to modify our Vlasov-Poisson equation. Now we have a scattering term here on the right-hand side. Before it was equal to 0, but now you have an additional term that would mean that particles could enter or leave your phase space depending on how it interacts. And that also causes, for instance, halos to become rounder and to be less centrally concentrated, as one shown here. Density is a function of radius. So the more self-interaction there is on the center, the less dense they become. Yeah. So I think there are many other cases, I was saying axion dark matters and neutrinos, primordial black holes, and I just wanted to give you a broad overview of what you can do with these simulations. I think it's okay. So these are kind of all speculative things, right? We say, okay, what if dark matter is this type of this other type? There are other things that we know that are there. One of them is that we know that there is variance in the universe, and so initially in the soon after inflation, you have the same fluctuations in both variance and dark matter. But then, as the universe keeps evolving, the dark matter does not couple with photons, which means that it evolves differently than variance. And by the time that the CMB, the last scattering surface, or well, actually recombination, you expect them to, variance and dark matter to have a different spatial distribution. So another area of research is trying to see whether one could detect this difference in variance and dark matter, and whether it could actually leave some observable signatures. And this is what is shown here. This is the power spectrum, the amount of clustering in variance and CDM as a function of scale. And then we see that variance are actually about 50% less clustered than dark matter at high redshift. But gravity couples them together, and then these differences kind of wash out. And, but they're not completely zero by today. But we have, for instance, you can test whether it's the same to evolve a single dark matter fluid or to evolve two fluids, one with dark matter, another with variance. And actually, this is another one of the assumptions that people have been focusing on, and actually validate that this seems to be the case, that this assumption is better than 1% or so. What seems to be more relevant is that variance interact not only gravitationally, but have hydrodynamic forces, can cool, and so on. And this is what we can simulate with hydrodynamic simulations, for instance, this Illustris, or Horizon AGN, or Eagle. So that actually changes quite dramatically the distribution of matter in the universe. This is what is shown here. This is the expected clustering of matter in the universe, including all these hydrodynamic processes, relative to the case where you consider only gravity. And you see on large scales, they are the same, the ratio is 1, but on small scales, they can be quite different. So, and how different depends on which simulation you believe, right? And all these simulations implement different hydrodynamics and subgroup physics, means like recipes for how stars, black holes form and interact. So this is kind of a relatively a big problem for numerical simulation, that we still don't know how to predict a priori the effect of variance in the distribution of matter in the universe. So I wanted to finish with some recap of the state of the art. So I think all this field of large-scale structures have been pushed by this continuous advance of observations. Now we have continuously larger and larger surveys that map a larger volume of the universe with fainter galaxies, and that has required a similar progress in the field of numerical simulations. So we want to be able to create simulations roughly equally big as these large-scale structure surveys, and be able to resolve even the smaller structures that appear in the smaller galaxies that are resolved in those surveys. We also want to improve our simulations, right? We want to do more accurate calculations, more sophistication, better accuracy, and so on, and also to tackle new problems that we have not been able to do before. And this is what has been driving the continuous increase in this in numerical simulations. And this is a plot showing you the number of particles that we use in our simulations as a function of year. This has roughly the number of particles in each simulation doubles every year and a half, roughly. And we can see this has happened from the 70s and so on. So this is actually quite remarkable, because actually computers have not gotten faster after 2005, 2010. Right? So you might notice with your own laptops, right? The computers don't get faster. What they do is that you get more computer cores in your CPUs. So that means like the computer architecture have continuously changing. So you need to adapt in your software development. So regardless of all that, this trend has continued increasing. And actually many, historically, I think the field of computational simulations have won this Gordon Bell Prize, which is kind of a prize given by high performance supercomputing. So it's one of the few codes in science that are able to exploit these very large simulations. Sorry, very large computer facilities. So we see also that recently now several groups have crossed the 1 trillion particle mark, which is, I think, has been a really big achievement for the field. Then with different codes, algorithms, and approaches, they be able to have these very large calculations, and they agree on also on the results. Yes, okay. So as I was telling you, these are kind of very, very tough calculations. Typically, some of the largest one, they have used between 20 and 500,000 CPUs. So these are really some of the largest supercomputers in the world. So there are a lot of computational challenges we need to address to be able to run these simulations, and I just split them into kind of 3 areas. One of them is that the most expensive part of these calculations is the calculation of gravitational forces, and then in that sense, they are now becoming very, very common to use accelerators like GPUs to be able to compute all the small-scale interactions. There are now the most popular algorithm for computing these forces is called the fast multiple method, similar to the 3 algorithm that I described to you earlier. How to deal, now you have this huge amount of particles, you need to represent them all in memory that uses hundreds of terabytes of RAM, so you need to also develop strategies to compress and use the minimum amount of computer resources, so only like that you can go and achieve these very large calculations. And the final one is the I/O, the amount of data that is produced and the amount of time that is spent. For instance, just to read the initial conditions for one of the simulations took approximately 200,000 CPU hours. So you've spent a lot of time just dealing with this data set. So that's another thing that is actively, I think, research on is how to maximize the output of these numerical simulations. And many times the success of a simulation is not only measured in terms of the direct scientific output, but as how widespread has been used and how many different research projects they've enabled. Okay, so running one of these simulations is hard, but if you wanted to use them for actually interpreting the neutrino mass, we will need to run hundreds of them. So that is actually super, super hard. So there have been like several areas of development that have tackled this. One of them is emulators. So the idea is to run an ensemble of tens up to hundreds of simulations with different physics, and then interpolate them in some smart way. So to make predictions as a function of your parameter of interest. And nowadays, I think they have this type of emulators have been built by different people around the world, and they tend to agree now at also percent level for the power spectrum as a function of cosmological parameters. Some of the challenges here is that because you need to run a lot of simulations, they typically use a small volume in parameter space. You cannot change too much your physics. So probably in the future there will be new ideas of how to improve the way in which we cover the parameters, the relevant parameter space. Same thing is with variance. So as I was telling you, variance do matter for the distribution of large-scale structure, and it's you might be tempted to think that the hydrodynamics is the ground truth, but it's actually it's important to be aware of all the limitations that this has. As I was arguing before, many of these simulations, hydrodynamic simulations, make specific assumptions about the subgrid physics, like how star. You cannot directly simulate how a star is going to form, so you come up with recipes. And usually those recipes change when you change resolution, or they've been calibrated to work on a very specific set of circumstances. So yeah, so there could be several drawbacks, and actually might not even give you the correct answer, hydrodynamic simulations. So there had been also the development of semi-empirical methods that try to either learn with machine learning, for instance, general features of how variance have changed the distribution. So then you can very quickly change the effective, for instance, efficiency of black hole feedback and so on. Or you can also try to develop more simplified description of what is the effect of variance in large-scale structure, and try to build emulators and marginalize over that too. So also, if we, another area is how to model correctly galaxy clustering, a distribution of especially how the galaxies will form and be distributed inside these dark matter simulations, and that yeah, well, I don't want to drag this too much. There's also a lot of developments on how we can, or one of the challenges is how to be able to do variance and astrophysics in a way that is robust for inferring cosmology. So actually, yeah, one publicity slide. This is actually what we're trying to focus in on in my group in Donostia. So we have numerical simulations of different cosmological parameters, and then we try to model in an agnostic way, like try to make minimal assumptions about how galaxies form and what is the role of variance, to then train neural networks that allow us to predict very quickly the distribution of galaxies and of a distribution of variance on large scales, so that they can predict directly different summary statistics and ultimately constrain various ingredients of the cosmological model. So if you are more interested, we have a website and where we have also publicly available several of the tools that we have developed. Okay, so my outlook, I think it's I think the field of numerical simulations have been developed over decades, and nowadays I think they're quite mature. It's a quite robust field that we understand very well. There are assumptions of the role of numerical parameters and how to get accurate results. But this requires progress in many different areas. For instance, the way in which we have tested basic assumptions, from the use of Newtonian limit of GR, of how we can discretize the phase space of dark matter. Also in terms of algorithms, the initial conditions, the time integration, also different force calculation and so on. So also it's I think also recently we have converged to understand better all these different details, and also have been super important extending the simulations to beyond lambda CDM, trying constantly different dark matter scenarios, different. I did not talk about this, but also about the law of gravity, the nature of dark energy, and so on. And also has been super important, I think, the reliability and openness of the field in terms of systematic comparison among different groups, where we have simulated the same region of the universe, and you can test directly the different predictions, and also having open source codes have also helped a lot, I think, in the field, and of course all this supported with a continuous development of high performance supercomputing, improving our algorithms, constantly keeping up with the largest supercomputers in the world. And as I was telling you, nowadays these simulations can run up to hundreds of thousands of different computing nodes. And I think all these have been like a preparatory stage for the next big challenge of numerical simulation, which would be directly interpreting the observations of the universe, right? I think these numerical simulations are the only way that we can access to this highly nonlinear regime of the universe. But for this, we need to address several issues. I mentioned briefly the role of galaxies and baryonic effects, and how we need to understand the uncertainties and develop more robust and accurate methods. we need to keep up with the development of HPC facilities. I think there's a change of paradigm in the type of architecture that supercomputers will use to get to the exascale. And I think we'll also we have to constantly keep up to date in that regard. And concerning cosmology variations, I think I told you about, well, I think we have also seen recently the development of fast methods for modeling gravity and also astrophysics, and the rise of emulators and machine learning that will allow us to take now these super expensive calculations and generalize them so then they can be useful for interpreting data. So if all this is successful, I think that embodied simulation could become like a key ingredient to try to elucidate the nature of dark matter, dark energy, and gravity that we will undertake in the next years. So thank you.
Hi, thanks for the nice introduction. I had an agnostic question, and perhaps this is exactly what you do in your own work group, that are there any efforts going on to figure out how degenerate the space of numerical methods is that reproduce the observed universe? So,
right. Yeah, I mean, I think it's a super important question because, for instance, if we have if we measure, for instance, the distribution of galaxies and the power spectrum, and then we want to claim that there is a signature of massive neutrinos, for instance, the kind of a suppression in the power spectrum. We want to convince ourselves and convince others that this suppression is really due to neutrinos and is not due to the feedback due to AGNs, right? So we need to actually be super sure of that any constraint that we give on fundamental physics is after marginalizing over all the uncertainty in astrophysics and, of course, also other cosmological ingredients. So yes, I think that is that's going to be a key issue. And to address that, I think will be super important to be able to quantify our ignorance, right? So quantify how what is the uncertainty associated with the way that we solve Newton's equations, the uncertainty due to galaxy formation, and only if we are able to do this in a convincing manner, I think we will be able to convince the rest of the community that we have made some important discovery. Yeah. So.
Is it going on?
Yes, to some degree. I think different people have different level of awareness, or they worry differently about this. But for instance, camels, they kind of try to do this in the sense of they vary cosmology and galaxy formation physics. So they would like to put, essentially, you say, okay, constrain neutrino mass after marginalizing over all possible hydrodynamics. I would say that you need to also marginalize over subgrid physics, for instance, and that, or that you need to go even beyond that and not even rely too much on hydrodynamic simulations. And you need to, my personal view is that you need to go to even more agnostic models. And so something we have been working on is combining ideas from perturbation theory with numerical simulations, where we can make minimal assumptions about, how galaxies form and so on, and try to let the data, the real universe, telling us how to, what is the correct physics. But at the end of the day, I think this is kind of an iterative process. I think we come up with our models, try to do our best job, we kind of compare against the universe, and as we learn more about astrophysics and so on, we kind of improve our models, and then hopefully we convert.
Thank you, Raul, for your nice review. My question was along the same lines, but more specific. So, for instance, in galaxy redshift survey collaborations, like in the dark energy spectroscopic instrument, DESI, the strategy is essentially based on having predictions of the dark matter field and then of the halo distribution given a particular fiducial cosmology, say, or a set of different set of cosmological parameters, and then do the connection with things like HOD, halo occupation distribution, to the galaxy distribution, so that you can be flexible. It has been shown in some studies that there's a degeneracy between the bias and the cosmology. So you can have a particular cosmology which would imply some 2-point and 3-point statistics, and then you can tune the bias to get starting from a wrong cosmology but ending up reproducing the galaxy distribution. So I'm wondering how you can tackle that.
Right. Yes. Yeah. I mean, I agree with you. And essentially, the problem is if you have your numerical simulation and we know how to do gravity, but then you put galaxies in a way that then its number is proportional to the halo mass, right? And then you say, hey, if I use this model, then neutrino mass is 0.1 eV. Then you need to show that these neutrinos are 0.1 eV and not that your galaxies depend not only on the halo mass but also on other properties, right? So yeah, so for me that I think is a fundamental problem when we're trying to use simulations for inferring cosmology. That's why, yeah, and I think it's something we need to tackle. And one way would be to try to have more generic descriptions of bias tracers, borrowing some ideas from effective field theory or from perturbation theory. To me, that seems to be the most promising way.
Thank you very much. Thanks. Very quickly, so it was my impression from the first slides that you introduced numerical errors at the level of like values between 1 and 10, say, within codes themselves and comparing different codes. So when you try to predict the baryon feedback effect, you have deviations in the same scales. So would you say the difference is more numerical or because of the different assumptions of the baryonic physics?
Right. So if we just do gravity-only simulations, I think you're right that the agreement is percent level up to k of 1 to 10. But that convergence is not absolute in the sense of that you can just improve the numerical accuracy of each code, and then the agreement improves, right? So if you reduce the softening, do your more time steps in your time integration, and so on. So in that sense, it's kind of we understand well that part. But when we go to baryons, then the issue is not numerical, right? It's really about what physics you implement, how you implement them, and how you calibrate the free parameters of your subgroup physics. And that the differences could be 30 times larger than the issue of gravity, right? So for instance, you can, one group might decide to calibrate against the stellar mass function, right? And then you tune your numerical parameters so that you reproduce the stellar mass function. And then, but then other group might tune in the gas fraction in clusters, right? And those differences lead to differences in the outcome. And then on top of that, then when you implement feedback, for instance, AGM feedback, there are different choices, and then and free parameters. So yes, I think it's mostly about the physics that you implement, how you implement them, and how you tune the free parameters of your physics.
Hi, thanks for the very nice overview. I had a naive question about the implementation of non-Gaussianities as the initial conditions. So if I had, for instance, initial conditions with an exponential tail, as many people propose for stochastic inflations and things like that, are the simulations aware of the full PDF of the perturbations or only of a few statistical moments beyond the power spectrum?
Yeah, and usually you implement different non-Gaussianities in terms of bispectrum and trispectrum. I'm not aware of any general algorithm that would put an arbitrary PDF. But yeah, I mean, usually you are in the limit where these non-Gaussian fluctuations are small compared to the Gaussian part. So I would imagine that anyway at first order, the impact of that particular model would be with a kind of bispectrum shape or a trispectrum.
Thanks.
At least one more question from Nestor.
Hello. So you mentioned that you have a review on dark matter n-body simulations. From your experience, let's say we have an n-body dark matter simulation that's collisionless and that is non-radiative. Is there any way that the dark matter would cluster, would clump if it cannot lose the energy? Or is there some other way that it could cluster by losing energy different than collisions or radiation?
I mean, to be able to collapse, you need to lose essentially angular momentum, right? I mean, I guess if you have, for instance, primordial black holes, that could actually, you could have mergers of primordial black holes. If your dark matter was made of primordial black holes, and that could actually collapse on very small scales. But to lose energy, I mean, you might have maybe some dark radiation that you might be coupled with. And
all right, we can also talk afterwards.
Yeah.
Thanks.
Okay, so let's thank Raul again while we switch for the next speaker. Who's coming?
We have a coffee break.
There's coffee break. Okay,
Then
sure.
we have the student talks later. Okay. So in half an hour we are back. Okay.
My mic doesn't work, I think.
Wait, because it's on? Yeah, he has to open it up, so don't worry.
Let's see. Can you test now? No. Yes, so maybe you have to switch off and switch on again. No? I think that this is what he's telling me. No? Yeah, no?
I don't know.
Yes,
Yeah,
now
no, it works. All right.
Okay. Yeah. So, welcome everyone for the last session of today's last session. We're going to be very strict as we were the other day, so we have 7.5 or 8 minutes for the talk, and then 1.5 minutes or 2 for questions. So, we start us off now.
All right. So, hello everyone. My name is Matteo Luca. I'm a PhD student at the Université Libre of Brussels. It's a great pleasure to open this second session of student talks, and I would like to do so by talking to you about a possible tension that seems to be emerging between the early time inference and the late time measurement of the matter power spectrum at small scales. And without dwelling too much on the details, because I hope you remember Matteo Ville's introduction, I would still like to give you a little bit of a broad-brushed introduction about the Lyman alpha as a forest as an observable of the universe. The theory is very simple. You have a very bright source of photons very far away from us, and along their way towards us, the photons travel through a series of hydrogen clouds, and within these clouds, the photons get absorbed by the neutral hydrogen atoms, and then they get statistically re-emitted in another direction with respect to the line of sight. And this leads to a series of absorption features, and the collection of these features then leads to what is known as the Lyman alpha forest. The intensity and the shape of these dips then gives you information about, for instance, the distribution of clouds along the line of sight, as well as the thermal history of the hydrogen. And with this information, when you have enough quasars, then you can build what is known as the one-dimensional Lyman alpha flux power spectrum, which is a mouthful, so I will just call it either flux power spectrum or power spectrum. And it's very comparable qualitatively to the better known matter power spectrum, just that in this case we are focusing on the hydrogen instead of the dark matter distribution. All right, so this is how the flux power spectrum looks like. Here is the dimensionless power spectrum. Here are the scales. And just to place the observable in the landscape of other probes that are testing the matter power spectrum, here we're really focusing on the smallest scales we have access to. And although we are at very small scales, I will still divide the spectrum into large scales here and small scales here. And that is because at small scales, you have a rather linear dependence of the spectrum on the K values. So it gives you a better handle on cosmological parameters like the amplitude and tilt of the spectrum. While at small scales, you are contaminated by thermal effects like the thermal broadening or pressure. And really, here, the cosmological information is masked by the late time thermal history. And this gives you information about the astrophysical parameters as well as the dark matter, as we will see. So to focusing on what is the state of the art of our understanding, what we can gain in terms of cosmological understanding from the Lyman alpha, starting by the large scales, we have an overall good agreement with weak lengths in surveys, like focusing, for instance, on sigma 8 and omega matter. But when we start to compare Lyman alpha to early time probes like Planck or BAO, we start to see in this omega m ns plane divergence between the red contour, which relies on Lyman alpha information, and the blue contour, which is instead representative of the early time information. And you might say, oh, well, but this is not statistically significant at all. Well, you would be right. But let me remind you that at such small scales, omega m and ns are impacting the matter power spectrum in the very same way. They are both tilting the spectrum. So in truth, this is just a one-dimensional tension. And to show this in this very, well, it's very deep reference that I encourage you to read if you have time. I wasn't part of it, but still good. Well, all right, okay. You got the meaning? What they've done is they split the spectrum in the tilt of the spectrum at CMB scales and Lyman alpha scales, and they recover perfectly the omega m value that you would like from Planck, but there is a clear significant difference in the determination of the scalar specular index. So you see, this is really a more than 3 sigma tension, and it's also confirmed by the chi-square improvement. So lower NS means that you are suppressing the spectrum with respect to what the CMB would predict if you fix the parameters at CMB scales. And although the same qualitative analysis is very difficult at small scales, you could still do some qualitative, like let's say, qualitative for the moment, just take on the message that over all Lyman alpha scales, the data is consistently preferring a lower NS value. And a lower NS value, as I said, is a suppression of the matter power spectrum. And this becomes very interesting because, as you might have heard like this morning or just in the talk before, many dark matter models predict. I've got 6. Well, OK. All right, sorry. Thank you. OK, all right. So 1 minute matters. I don't have many. So you have different models predicting different suppressions. And you can go from very shallow suppressions, like in the feeble interacting dark matter model, to a mixture of warm dark matter and cold dark matter models, where the suppression is very sharp. And in between, you have interacting dark matter with baryon or, say, neutrinos. So what we have done is to look at these many models and which encompass the different possibilities and compare them to data, trying to see what models might fit the bill in order to solve this tension. And although the results are very interesting, in the case of warm dark matter and field interacting dark matter, they are you don't have any preference just because they are either too shallow or too sharp, and you cannot mimic the effect of a lower NS value on the matter power spectrum. But in the case of both interacting dark matter scenarios with different significances, you find a preference for a non-zero interaction strength in both models. And in the case here, I just plotted the case of dark matter neutrino interactions. You have a preference which is 3 sigmas away from 0, and this really reflects the constraining power of the data. So to conclude, well, OK, this is the graphical representation. Here in black is again lambda CDM, and you see that in particular for this redshift bin 4.6, you are consistently doing better in the dark matter neutrino and dark matter baryon interactions. So to conclude, what we know is that there is a 2 to 3 sigma tension in the determination of the matter power spectrum tilt between early time inference and Lyman alpha measurements. We know that there are some dark matter models that might fit the bill, which is very exciting, but there is a lot we don't know yet. For instance, we don't know if this tension is even real. The significance is in this limbo where you could say it's nothing or it's something interesting. So we would need to combine more data sets to compare the numerical pipeline to find the preference. At the same time, we have this suppression, which is consistent with the lower sigma 8 value. So are we talking about 2 separate tensions? Is this just one tension that covers all small scales? It would be interesting to find out. And then at the very end, let me point out that here we focused on dark matter, but you can really have many models like modified gravity, inflationary scenarios, which are modifying the spectrum at small scale. So it's not exclusive to dark matter. Every model that mimics the effect of NS could fit this Lyman alpha data. And with that, I conclude. Thank you very much for your attention. And
perfect timing. Thank you.
Yeah, thank you very much.
Questions for?
Hi, Matteo. Thank you very much for the super nice talk and fun talk. These people try to solve this tension by considering 2 different scalar spectral indexes, right? One
yes.
of the, I mean, is what if they didn't they try to add just a running?
Sorry,
a running in the analysis.
Yes, and I think they find
did
the
also.
same. Yeah, I think they find a
okay.
Exactly.
Yeah.
Exactly. It's something you could do as well. Yeah. I think the problem is that let me see. I don't think I have a. Oh yeah, we can try to do this. I think the running is doesn't suppress it as much, I think, but you can certainly find some modifications of the matter power spectrum which are unrelated to dark matter, which might have some sort of suppression. So yes, you're perfectly correct. This would be something you could do.
Okay, thank you very much. Thanks.
Yeah, it's perfect for us.
Thanks for your question. Olga, any other question for Matteo? We're done.
All right, thanks again.
How does this work? Ah, es al revés. Okay. ¿Dónde está? Uy, sorry. Oops. Okay, what is the pointer? Ah, okay. Sorry for the mess. Yeah, sí. Okay, hello. I'm Lourdes Ondaro, PhD student at the University International Physics Center. I will be talking to you about simulating the first halos in warm dark matter cosmologies. So, as we have already heard a lot of times in this school, dark matter, it free streams in the early universe because of its thermal velocities, and it washes out perturbations under a given scale. These imprints are cut off in the power spectrum of the warm dark matter, and here you see as a solid line. Unlike the case of cold dark matter, right, where we have perturbations at arbitrarily small scales, here in the dashed line. So this means that from the point of view of structure formation, in warm dark matter there will be a minimum halo mass. We won't form halos under a given scale, and we call the mass of these halos half-mode mass halos. But to gain a bit more of insight on how the formation of these mass halos is different in warm and cold dark matter, let's see a bit of images of a first halo in warm dark matter and the formation in a CDM equivalent. So in CDM, you see that small perturbation collapse and then merge to form larger ones, while in warm dark matter, the smooth field collapses directly to the halo, right? So the formation is very different, and one may ask whether the structure of these halos, the inner density profile, is also different or not. So some people have, this is another snapshot. So some people have asked these questions and have even answered it for a very specific type of warm dark matter, or well, in this talk I will call warm dark matter any power spectrum that has a cutoff, no matter the scale where the cutoff is. So for the case of the 100 gigaelectronvolt WIMP, they have simulated this. In this case, the first halos are like Earth mass halos, so super small, 10 to the minus 6 solar masses. And they have done this simulation in two different cases, where they put in a cutoff in the power spectrum and without. So the green case, this is the logarithmic slope of the density profile of this halo. So the green case is like a CDM-like, so without a cutoff. And you see that it follows the very well-known shape of the NFW, if you have listened. So basically, in the inner part, it goes asymptotically towards -1. However, you put a cutoff, you find this blue or red behavior. So it's like a cusp in the inner part that is super steep, and the behavior is super different from the other case, right? So the question that we are trying to answer in this work is whether this is a very specific behavior of the WIMP case, of this cutoff, or it is general to any cosmology with a cutoff in the power spectrum, no matter the scale of the cutoff or the shape it has, or what is the slope of the power spectrum in the cutoff. So that is what we will try to answer. And to do that, what do we do? Okay, so we basically run simulations, embodied simulations of the formation of these halos, and we look at the structures to figure out whether what is the case. But it's not so easy because embodied simulations are not perfect, and they have some problems like the artificial fragmentation, and we will need to solve the equations in another way that don't suffer from this problem to see if our results are robust. So this is our set. We have 16 halos at the half-mode mass. We have varied a lot the warmth of the dark matter from 250 eV to 5 kV, that is still observationally viable. And this means that the masses of the halos will vary from 10 to the 12 solar masses, so Milky Way-like, to 10 to the 7. Let's see one example of those. So this is a halo of the 1 kV. So this is the density field, and in the right I show you is the density profile multiplied by r to the 1.5. This means that if here you see a horizontal line, the density profile will be proportional to minus 1.5, so very steep. So let's go. The sheet collapses directly to the halo, and in the moment the halo forms, we have this steep broken power law-like structure with like this cusp. And as the halo grows, this doesn't really change, right? The cusp stays there. So it looks good. Another way of looking at the same thing, maybe less beautiful but more practical, is this plot. Here, this is the halo that I have just shown you. I show you it's alpha, that is the average slope in the cusp. So I take in each snapshot the average slope of the cusp at different peak height values. So in this, for a given halo, at different moments of the collapse. And you see that it's horizontal, so it's not like it's a stable solution. Yeah, and it's very steep. So now I will overplot all the other halos. And you see that the color is the warmth of the halo, so there is no any evolution. They all fall in the same region of this minus 1.5, 0.6. So this means that the formation of the cusp is not really like dependent on the specifics of the cutoff or the collapse, but really given by like the gravitational collapse from the smooth field. Like it's a very deep or like the effect of the gravitational collapse itself. So we are happy, okay, but not so happy because are we sure about the results? Because we have used n-body simulations, as I've told you, to get this plot, but n-body results have problems. That is, one of them is artificial fragmentation. So to understand it, let's look at these images. This is a filament before the collapse of the halo. So as in warm dark matter, there is no small scale structures that are suppressed, but here we see some. And these are the effect of numerical errors that we do in the first computation, that then they pile up in different time steps, and they form these artificial clumps that they shouldn't be there. They are not physical. So, but we get them, so then they merge and they form this halo. This is a very unphysical process. This should be a smooth collapse, but it is not. And in fact, it can affect our results. And it may affect, because, for example, this is the same kind of plot of before, and in the inner part, we see that it's not the cusp, but it goes down. So we have to understand this better. And to do so, we need some simulations and to suffer for artificial fragmentation. Now I don't have to explain how we do this. Raul mentioned them. There are the phase-space tessellation type of simulations. And if you have some, you want to know more, like ask me later. But the take-home message is that we have some simulations that don't solve the Blasov-Poisson equation, but without, like, with another mechanism, and we don't have artificial fragments there. So we simulate the same formation of the same halo, and it looks very different, right? Here is smooth, and yeah, it's super different. So let's look at the density profile, and here the dashed line is the n-body result, and the solid line is the sheet and release results. In the inner part, we recover the cusp. So this means that the artificial fragments are having an effect, and the n-body gives us the wrong result in certain regimes. Okay, so with this, I leave it to you with my general conclusions, but I give you like a last take-home message. That is that the inner cusp that we see in the first halos in warm dark matter, we see them in all of the first halos, so no matter the scale of the cutoff, that it is a direct effect of the gravitational collapse from the smooth field. And if there are mergers in the process, no matter if they are physical, like in a cold dark matter case, or numerical, in the artificial fragments case, this inner cusp is shallow. So I think that in this way we have somehow gained a bit more insight on which are the important processes that really set the structure of the halos that we see in the universe. And that's it.
Thank you, Lourdes. Question for Lourdes.
Hi, thank you very much. It's not a question, it's just, so I don't know, I mean, since you have all the machinery, could you do this study about the formation of halos, for instance, also in action like dark matter models, very, very light dark matter models with actions with, in this
yes,
string
but
Axiverse
there
universe?
the equations that to solve are different, right?
Yeah, sure, of course, but I mean, since you have the machinery, I think that it would be also very interesting because, to see how differently are formed the halos.
Yeah, I guess, I don't know if in action like dark matter, if the artificial fragmentation is an issue, because this comes mainly because in warm dark matter, you don't have power in small scales, no? So artificial fragmentation, you have it also in cold dark matter, that is not relevant because you have real physical power. So in action like you have power also in the small scales.
I think that there may be what changes is the redshift of formation of these halos. They form later, I think.
In action, like.
I think. But it's just a suggestion. Since you are the expert. Thank you very much again.
Thank you, Olga. I think we have no more time, right? So we'll switch to the next speaker. Thank you. Thank you, Lourdes.
Can you hear me? Yes, okay, yes. Hello everyone, my name is Alex. I want to talk about the experiment called Ptolemy, which we have already heard about today. This is an experiment of relic neutrino detection. I want to present my work made in collaboration with a postdoc of mine, Evgeny Chepish, and two professors, Dim Chiyanov and Alexei Boyarsky. So as we all know, the universe is filled with relic neutrinos. We expect about 340 neutrinos per centimeter cubic in this room right now. And similarly to CMB, we could expect that these relic neutrinos may shed light on our universe at times such as 1 second after the Big Bang. So it's indeed a very ambitious goal to catch them. So how do we detect relic neutrinos or any neutrinos? Neutrinos participate in weak interactions, so the most obvious way to find them is in proton to neutron conversions or beta decays or inverse beta decays. So what do? We know that if neutrinos are massive, okay, not like we know that if neutrinos are massive, and they are massive, we expect that near the endpoint of our beta spectrum we have such a small deviation from a straight line. And inversely, if we capture a neutrino, then it would give us more energy that what we can get from the beta decay. So we expect a small peak after the endpoint of beta spectrum. And searching for this peak is basically the goal of our experiment. Okay, and we immediately have a lot of problems, which first of all choose a proper isotope for our experiment, and also we have a problem that if you just put a lot of isotopes in your box, then your electrons emitted in beta decays would just scatter off other atoms. And that's very bad because we want to measure the energy very precisely. And if you want to overcome this problem, you need to make either a very large scale experiment, like 10 kilometers diameter, or you need some other options. And Ptolemy proposes the option to put our isotopes on, to absorb our isotopes on graphene sheets. Okay, so basically that's it. Our experiment, initially it was proposed to use tritium as a beta decay emitter. You put it and it is absorbed by graphene via van der Waals forces. We expect 3 events per year for 100 grams of tritium, and to measure the end point of the spectrum, we need very high energy resolution of order 10 MeV. And immediately we encounter a lot of problems. We not only need to measure energy experimentally with such high resolution, we also need to control the energy broadening, the intrinsic energy broadening, which comes together with adsorbing of our isotope to a graphene sheet. And as was shown in this paper, when you put your isotope in this almost harmonic oscillationary potential, it starts to do zero motion, and due to Heisenberg uncertainty, it has uncertainty in momentum. And it has been shown that this uncertainty in momentum introduces 300 MeV uncertainty in energy, which is much larger than what we need for relic neutrino detection. And we have two options. We can either modify this potential here, which is not very good because you need somehow to change the properties of graphene. Or we can use another isotope, which is much more larger, and therefore it experiences much less uncertainty due to Heisenberg principle. And this is the list of possible candidates which we can use. They were chosen in order to have sufficient capture rates for relic neutrinos, and also not to have unstable daughter isotopes and so on, in order, because it can introduce additional backgrounds and spoil the whole experiment. And for nickel, we can immediately use the estimate which we have for tritium, just changing the numbers, just changing the lifetime and the Q value, which is the maximal energy which an electron can have in the beta decay. But we also want to know what is the capture rate for thulium, and here we have a problem because thulium does not experience allowed transition, it experiences forbidden transition. What does it mean? Let us look at the weak interaction Hamiltonian, and first of all, let us relate decay of an isotope and neutrino capture rate. You can get this simple result that your d gamma over dE contains a phase factor just coming from lepton momenta and some matrix element computed with this Hamiltonian. And Rayleigh neutrino capture cross-section has a similar form with the same matrix element. And if you have allowed transition, it appears that your matrix element can be is a constant. Why it's a constant? Because in nuclear processes, leptons, the energy scale of nuclear processes is of order 1 MeV, and the size of a nucleus is of order inverse GeV. So the wavelengths of your leptons is the wavelengths are much larger than the size of the nucleus, and therefore the nucleus doesn't know about kinematics of your leptons. The momenta cannot probe the internal structure, so this is just a constant. And with this approximation, assuming that we have an allowed transition, we get this result for thulium. And the problem is that for forbidden transitions, we cannot make this assumption because the nuclei have different, the initial and final nuclei have different different spins, and therefore your leptons have to carry angular momentum. And when they carry angular momentum, they have wave function which is suppressed in the origin. So the probability to emit such leptons is suppressed by this factor p times r, which is smaller than 1. And when you do this and account for different dipole, quadrupole emissions, you get some functions which are multiplied by some momentum, nuclear momentums of your isotope. And because there are many of them, you cannot extract them from lifetime of your isotope. And therefore, you cannot just take your data from nuclear table sheets and compute the answer. Therefore, we propose to measure it directly from the spectrum. And here we have a formula for experimentalists how to do it if you have some data in energy bins. We also made some prediction using a software called Beta Shape, but it accounts for electromagnetic corrections and also cannot compute nuclear constants. And actually, the spectrum has been already measured in EPFL, and it agrees with theoretical prediction from the software. So basically, we know the answer. And here are the answers for tritium, for thulium, for samarium. It should be nickel, apparently. And these are the expected sizes of your experimental target. And we also have a lot of other problems to deal with, but that's for the next talk. Thank you.
One question for Alex. Oh.
So if I understand correctly, the problem with the tritium is that it's so localized in the graphene, right, that then Heisenberg's uncertainty relation comes to haunt you. So do you actually need the tritium to be so localized, or is that just a side effect from the way it's set up on these graphene sheets?
Well, we need to localize tritium because of the whole concept of the experiment. We need the graphene sheets to put tritium there, then it emits electrons somewhere in the perpendicular direction, and then we can catch it with electromagnetic fields. So we need somehow to bound tritium to graphene. And actually there are two potential wells for tritium, but actually I don't remember why exactly this one was considered, I would suppose that for this one we would have even more energy uncertainty. So yes, like if we don't put tritium inside these potential wells, we wouldn't just get tritium adsorbed.
Okay, thank you, Alexei. Let's move on to the next talk by Catherine Nippel.
Thank you. Okay, good. Does it work?
Yes.
Okay. All right, yeah, I'm going to go right in. So my name is Katrin. I'm a PhD student in Aachen. And I work on machine learning approaches to indirect dark matter searches, and with this project specifically in the search for dark matter subhalos. So in principle, we know that there must be galactic substructure in dark matter from n-body simulations, and we call this dark matter subhalos. And of course, we want to search for them, so we must somehow assume that we're going to have a signal from this. So assuming a WIMP paradigm, we could get annihilation from dark matter into standard models, which would then give rise to a photon flux, specifically in the gamma ray range. You can see this on the figure I show you here on the right for two different channels in annihilation channels in the standard model. And you can see also from the order of magnitude and the energy range that this should be, or this could, as a signal, be detected with Fermi-LAT. So we're using the Fermi-LAT 4FGL source catalog, so this is the point source catalog, to see if such a signal from dark matter subhalo annihilation might have already been detected. And we do this by in three main steps that I outline here. So we want to understand what our subhalos would look like. So we create a set of simulations. We assess the detectability really with the whole Fermi-LAT detector simulation setup. And then we want to look for subhalo-like spectra in the Fermi-LAT unclassified sources. So assuming the model that we put in. And we do this with a machine learning approach called Bayesian neural network, which I will get into in a second. But first, how do our subhalo simulations look? You can see over here the most important formula for this. So this is the flux in gamma rays from dark matter annihilation. And I'm sure you will see this again in Francesca's lectures. And you can see here there's two main components for us. That is first the particle physics part, or the dark matter model dependent part. So we have the annihilation rate, and we have a prefactor that is depending on the annihilation cross-section and dark matter mass. And for this, the NDE, we use the Poor Particle Physicist Cookbook for Dark Matter Indirect Detection, which is a mouthful, but I actually love the title. And then also we have the astrophysical part, or the halo model dependent part, and that is the J factor. So the J factor is the line of sight integral of the dark matter density squared. And for this we use the simulation tool called Clumpy to get the J factor and the positions of our subhalos. And then finally, as I said, we want to go through the whole simulation of the detection, so we can really have the systematics of the detector, and we can have really assess the detectability of the sources. And you already see some results here for one fixed dark matter model where the parameters are given here. This is a pretty standard model in the, as Tracy said this morning, traditional WIMP window. So we have 80 GeV dark matter, annihilation into BB bar. You will notice that there's a quite high annihilation cross-section. This is for good reason, because we want to have this as a part of a training set for a machine learning approach. We want to make sure we have quite a high number of detectable sources, of which we can then understand what the annihilation or what the fluxes would look like compared to our astrophysical sources, which are also shown in the plot over here in the green, which show all of the Fermi-Lat sources. And just as a slight addition, you can see here our detector simulation approach. This is quite standard, so we use FermiPy. We model ROIs around our subhalos. We include them, we fit the whole thing, and we get the detection threshold. And with this, we really get we get control over the number of detectable sources depending on the dark matter model. So this was the first methodological part of my talk. The second one is introducing the machine learning approach. So you will have seen a dense neural network before, I'm sure. I mean, we saw one in the first talk this afternoon. And with Bayesian neural networks, the specific part is that we exchange all of these nodes, which would usually be just fixed values, by weight distributions. And we let the network learn exactly also the uncertainty in the prediction by modeling the posterior distribution with this approximate weight distribution with the Kolbeck-Leibler divergence. You can see this simplifies a little bit, so it's really tractable and computable by the machine learning approach. And in practice, we use the flip-out estimator. If you're interested, this is an algorithm for this kind of thing that has been developed by Wen and collaborators in 2018. And with this, I can already show you some results. I will not show you all of our results, just for time reasons also. But one of the main things is we want to make sure that our network works very well. And we can see here the confusion matrix of our approach, where we have a binary classification of Fermi-Lat sources versus dark matter sources. We get an accuracy of 92%. So what do we take away from that? This is a typical accuracy which we would also get if we classify different astrophysical sources with a machine learning algorithm. This is, first of all, a good news that our network is doing a good job generally, but also that our simulations are not too artificial, but really realistic, so that the network is still limited by the statistics in the data. And then we also want to understand what we can learn about the subhalos. So in this plot where I show the beta plot, it's called, it's a plane of the beta and the peak energy of a log parabola fit. You can really see how the two classes separate, but still are somehow overlapped. So on the left, you see the 4 FGL sources in the colors, and for this, of course, the network label should be 0, and this is pretty much always the case. For the dark matter on the right panel, it should always be 1. There's some overlap where the network doesn't really do the right prediction, but we can use the network to really make sure we catch these cases where the network is not really doing the correct thing. And you can see in the uncertainty that we also get from the network that the higher uncertainty regions overlap also with the incorrect predictions of the network. So this really helps us make sure we get good predictions of our network. And then to conclude, and to get you also hyped a bit maybe for our results when our paper comes out next month, we really model for different dark matter models, not just this initial setup that I showed you just now, the subhalo population, and see how many detectable sources we are, and how our network can classify between dark matter subhalos and astrophysical sources, to then apply this on the unidentified Fermi-Lat sources to see how many dark matter subhalos or dark matter-like spectra we could have in the unclassified sources from Fermi-Lat. Yeah, thank you very much.
It does. You're modeling what a subhalo would look like in the gamma ray sky, right? And you pretended to distinguish it from other astrophysical sources. You have modeled the subhalos, their gamma ray emission. don't you need to model the astrophysical sources as well for the neural network to distinguish between the two, or is it just apparently it's just necessary to model the real gamma ray sources from dark matter decay? But are you modeling the astrophysical sources?
No, we just use the Fermi-Large point sources that were the most recent data release of the 4FGL catalog to compare to.
Okay, we may chat more detail later. Okay. Thank you.
Vale. Y por supuesto, sí, gracias. Good afternoon. I am Boris Betancourt, and today I would like to talk to you about the project that I have been researching during my PhD in this presentation named Proton Capture in Compact Dark Stars and Observable Consequences. So I would like to first start with an introduction. We know that dark matter is one of the most important open questions in contemporary physics. There have been several theoretical proposals and experimental efforts to determine what it is. The two most important related to the work that I will present today are the following. On the left, we have the proposal of massive compact halo objects that we know a bit from today, which states that there is perhaps no new dark matter particle, but rather the missing energy content is in the form of compact objects that emit little to no radiation, such as primordial black holes or Jupiter-like planets, that could only be detected through gravitational microlensing. What we took from this idea is that there is perhaps a particle dark matter, but it itself is in the form of compact objects, namely compact objects made out of dark matter that we have since labeled as dark stars. I would like you to keep this in mind then for the next part, which is the research into dark matter capture in stars, which assumes that there might be an interaction between the standard model and the dark sector. And as such, stars such as our sun would be able to capture dark matter, which would then populate their cores and annihilate and produce neutrino fluxes. Well, if you remember what I told you about the dark stars and assume that there is an interaction between standard and dark sector, then the dark stars would be able to capture standard model matter, which would populate their cores and then emit radiation according to well-known emission mechanisms. And as such, we asked ourselves the question then, could these dark compact objects I have previously mentioned be detected by means other than gravitational? Then I would like to summarize the main idea here in my general objective, which was to establish a theoretical model for the emission of electromagnetic radiation due to the capture of standard model matter, in this case protons and electrons, by a star formed by dark matter. And how did we approach this problem? We separated it into 3 steps. The first one, we wanted to figure out the capture of these new exotic objects I have been proposing. Secondly, how many particles would they gather per time? And finally, what would be the consequence of this population of standard model particles in the dark star? Let me move a bit into the details of each step. First, the structure. Here we relied very carefully on the interplay between particle physics and general relativity. From the particle physics side of things, we assumed a very simple self-interacting bosonic dark matter model. The particle theory gives us an energy momentum tensor that we could then utilize in Einstein's field equations, which would yield a system of coupled ordinary differentials equations that rule the structure of these dark stars. We solved them, of course, and I present some solutions on this plot on the right. The most important things that I would like you to keep in mind is that these stars are indeed compact. They have around 1 kilometer radius, 0.1 solar masses, very high temperatures, 10 to the 12 Kelvin. I would like you to keep this in mind for what comes next, and very large densities. So we have a structure. How many particles would they be able to gather? We based ourselves on the capture formalism introduced by Andrew Gould in the 80s, which is a very simple physical principle which assumes, for instance, that we have a particle incoming, in this case a proton. It will interact with the dark matter particles of the star. It will lose energy. Its velocity will be lowered, and as soon as the velocity is smaller than the escape velocity of the star, it will be captured. That is the physical principle, and it relies on 3 main components. First, the structure that I previously mentioned. Secondly, the surroundings, that is, how many particles are there in the surrounding medium for the star to capture.
And finally, the most important part, that there is an interaction between dark matter and proton. And here I give an order of magnitude estimate. However, what's important comes in the next slide, which is the radiation. So we have a particle population within the star. It will thermalize very quickly with it and populate its core within a special distance called the thermal radius. And from this thermal sphere, they have two ways of emitting radiation, photons. First, thermal Bremsstrahlung, which is due to the interaction between the protons and the dark matter particles that causes them to be accelerated and lose energy according to radiation. And finally, as soon as the radiation itself thermalizes with the whole system, we have the well-known result of blackbody radiation. So we have some emission mechanisms. Then how does this look like in terms of the luminosity that we would expect from such an object? And here I present one solution. You will notice, for instance, here I have luminosity versus time. And you will notice we have three distinct regions. First, we have a gradual rise of the luminosity. This is when the spectrum is Bremsstrahlung and the luminosity is increasing as much as there are new particles incoming into the star. Afterwards, you will notice this transition region where the max luminosity is reached, a very peaked part of the luminosity curve. Here is where the spectrum changes from Bremsstrahlung to blackbody, and we reach the maximum luminosity, for instance, in this case, over 10 solar luminosities. And afterwards, we have a very sharp drop of the luminosity. This is after thermalization. The star loses energy, as we know, according to the Stefan Boltzmann law of blackbody radiation by this T⁴ scaling. And if you remember, I told you that the stars have very large temperatures. So a lot of energy is emitted, and as such, the luminosity drops very sharply. Then we asked ourselves the question, okay, we have some luminosity. Then what could we say about detectability? Then if you take the previous profile I have shown you, you would, and assume that the dark star was formed 10 gigayears ago, then it would today have a luminosity of 0.1 solar luminosities with a spectrum, thermal spectrum, centered at around X-rays. And according to the figure I show behind me, this would be within observational capabilities. We can go even one step further. Assuming that the fraction of dark matter in the form of these exotic dark stars is 10 to the -7, we would expect to see at least 5 such events. However, here is where I want to stress something out. What I showed you previously in this time evolution of the luminosity, while the behavior is general, the value of the maximum luminosity, this is parameter dependent. So how big the luminosity will be depends on parameters of the model, such as the dark matter mass, the interaction with the standard model, or the self-interaction. And as such, for a good, advantageous set of parameters, then we would expect some signals. However, if there was no detection of such things, we would be able to set constraints on parameters of dark matter. And with this, I would like then to summarize what I have told you about. So what have we done? We have analyzed a scenario in which this dark star formed by dark matter interacts with protons. As I previously mentioned, parameters may change, but the principle that they will emit electromagnetic radiation is fact, and will open a new possibility of detection of compact objects like this by means other than gravitational microlensing. And as an outlook, well, I have told you about these compact objects that inject energy into their surroundings. Then there might be a possibility, if these stars were formed early enough, to see an indirect signal of their existence in terms of cosmological reionization, which is what we're working on. And with this, I approach the end of my presentation. I would like to thank you very much for your attention.
Questions?
So is it clear if you have a dark matter model, which, you know, in your case, it forms the materials, right? And it also has an interaction between the standard model and the dark matter sector. Yes. Is it clear that this type of signal would actually be the first way to see it? I mean, because you can also look directly for the materials, right? And you can also directly look for the dark matter standard model interaction. So is the parameter space where you get your 5 events here, is that still completely open from the point of view of the direct searches for this dark matter?
Yes. Yes, so basically,
clear why? Is it clear, like, why intuitively why this is the strongest signal to look for?
No, I never said this is the strongest signal to look for. So basically, what we asked ourselves is, we have this model, we have a dark compact object, and what would be the signal that we would observe from it other than gravitational? If it's dark matter, and assuming, of course, we don't have any self-annihilating dark matter, so asymmetric dark matter,
And this would be the signal that we would observe.
But I can look for this also, because you need a dark matter standard model interaction here, right? Which is not gravitational.
Yes.
So I can look for that also, say, in direct detection.
Yes.
So why is this a better probe than direct detection? Or for what properties of the dark matter is this the better probe than direct detection?
The better probe for direct detection. I don't think I ever made such a claim that this was better than direct detection, but what this would allow us. No, sorry, I don't think I don't think this would be a better probe than direct detection, so I cannot explain this.
Well, okay, so what? Maybe let me just rephrase the question, right? Because if basically if you say that the parameter space gives you the signal, right?
Yes.
If that is not yet excluded by direct detection, right?
No, it is not direct.
Yeah.
No.
Right. So then exactly. So then you're saying for this particular parameter point that you're looking at, your probe is actually the better probe because otherwise direct detection would have already found it, right?
Yes.
So I'm just kind of wondering what type of models are kind of more suited for this and what type of
Okay,
models
so for
are
instance, in this case of direct detection, we know that we have this direct detection is constrained from the lower part by this neutrino background. And in this case, we use an interaction between dark matter and standard model that would be able to probe below this neutrino background because there will be no such signals. So this is one of the advantages of this model.
Okay, yeah, maybe we can keep discussing later. And thank you very much, Boris.
It's not set up.
It's not set up. Is it falling?
Yeah. Because of my specs.
Yeah.
Yeah,
One
it's.
thing is that it lays on your ear. Does it lay on your ear? I cannot really see. Let me just tighten it a bit. No, but this is maximum. I cannot tighten it.
Yeah, I think it's done now. Yeah.
We'll give you a 2 minute. 2 minutes are left.
Okay.
After 6 minutes, we'll give you a 2 minute warning.
Okay. 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 Good afternoon. My name is Trisha Sarkar. I am PhD student at Indian Institute of Technology, Jodhpur. So my work is based on neutron star and its cooling. So I will start with a brief introduction of the stellar evolution. So stars are formed from the giant molecular cloud of hydrogen. So they are collapsed under gravity and form a main sequence star. So if the mass of the main sequence star is about very low, below 8 solar mass, then the star is evolved to a red giant, and from that a planetary nebula is formed, and from that a white dwarf star is built. And if the mass of the main sequence star is within 8 to 20 solar mass, then the star is evolved to a red supergiant. From this, a supernova explosion is occurred, and from that the core is formed as a neutron star. By the same procedure, a black hole can be formed if the mass of the main sequence star is more than 20 solar mass. So back to neutron stars. So the matter inside the neutron star is extremely critical, extreme conditions, like with very high magnetic field, high temperature, and extremely high matter density. So the internal configuration of the neutron star core is still unknown. It's still an open problem in astrophysics. So from several astrophysical observations and different terrestrial experiments, like different nuclear physics experiments, the determination of the core of the neutron star can be estimated. So one of the most important channel of determining the equation of state of the core is by studying the thermal evolution of the neutron star. So just after the birth from the supernova, the neutron star acquired a temperature of 10 to the power 11 Kelvin. So after a brief period of about 10 to 100 years, the core and crust of the neutron star is thermalized. That is, a very small uniform temperature gradient is set up within the star. So starting from that, after a period of about 10 to the power 5 to 6 years, the star cools down by the emission of neutrinos via the Urca process. So if the neutron star is very massive, like its mass is above than 2 solar mass, then it cools down direct Urca process, which is basically a set of beta decay and inverse beta decay reactions, both of which emit neutrinos. So for this reaction to occur, the proton fraction has to be above a certain critical value, for which, this condition has to be satisfied. So if the mass of the star is a bit lower, much close to 1.4 solar mass, then the direct Urca process, which is responsible for the fast cooling of the star, cannot occur, for which the star cools down by modified Urca process, which is also the a beta decay and inverse beta decay reaction, but here this bystander nucleon is present. This is a much less efficient process than this process. So a bit of nuclear physics. Okay, so these two quantities are introduced here. This is symmetry energy E-sim, and this is the slope of symmetry energy with respect to baryon number density, which is denoted by L-sim. These two quantities are very crucial parameters in determining the cooling of the neutron star, because they set up the how much should be the proton fraction inside the star, which in turn determines the cooling rate of the star. So most of the equation of states which are till now settled, they cannot accommodate the presence of direct Urca process, because they cannot produce sufficient amount of proton fraction in the low mass stars. So our recent data has been observed from the PREX-2 experiment. PREX stands for lead radius experiment. So that basically measures the skin thickness of the neutron. So from that, these two quantities has been estimated, E-sim and L-sim, whose previous estimation were these values. So specifically for this parameter, L-sim, its value has been obtained to be pretty high. There is very much difference. So with these new values of these two parameters, we construct the equation of state of the neutron star core matter for both core matter, and from which we determine the cooling rate of the star. Okay, so in this work we have taken the three model stars of masses 1.2, 1.4 and 2 solar masses, which are governed, the core of them is governed by two equation of states, DDMEX and GM1. They are pretty famous in the domain of astrophysics. So this is the NC is the core baryon number density, which are found to be this, and R is the radius of the stars, and RDU is the critical radius above which the direct Urca process in the star occurs, and NDU is the corresponding critical baryon number density. So the results are determined for both superfluid and non-superfluid matter, as we know that there is a possibility that neutron star matter is also superfluid. Anyway, I'm not going in the detail of that. So for both superfluid and non-superfluid, these estimations were found to be nearly similar. And these are the final results of the work. These are the cooling rates. This is temperature in Kelvin, and this is the time in years. And these three are the cooling curves for three different stars of different masses. These more steep curves, these are for the non-superfluid matter, and these less steep curves, they are for the superfluid matter. So we can see that for this non-superfluid matter, the cooling occurs very fast, while for the superfluid matter, the cooling rate has been much lowered. And these numbers, they represent some very well-known isolated neutron stars, and their temperatures, that is their thermal properties, they are well adjusted with our theoretically predicted cooling curves. So, yeah. So at the conclusion, I can say that with our result for the new from the data obtained from the PREX2 experiment, even the low mass neutron stars, like having mass 1.2 solar mass, they can exhibit fast cooling, which is in contrast with the previous case where the more massive stars only could exhibit fast cooling process. And we showed that our equation of states, DDMEX and GM1, with them, a number of isolated neutron stars, their thermal properties are matching with our theoretically obtained curves. So, thank you very much. Yeah.
Keep turning this off. I shouldn't turn this off. No questions for Trisha? Yeah, there's one there.
Hey, I'm just thinking, like, now with these new cooling curves that you have, is there a way to kind of kind of independently get some indication for this? I'm thinking, okay, what I have in mind is something like gravitational waves, right? Because gravitational waves also will be able to measure the equation of equation of state of the neutron star.
Yes.
So I'm wondering what would be the interplay of future gravitational wave measurements and these results. Can you say something about that?
Well, with gravitational waves, yes, you can constrain the equation of state of the stars. And just by using those equation of states, actually there's a very quite well-known software for this, for generating cooling curves. So you can just put as an input those equation of state in the software, and you can, get the cooling curves from that. So that's it.
Yeah, I have a related question very quickly. So you mentioned a new experiment. I think it's PREX. It's called.
PREX. Yeah.
It's a nuclear physics experiment, I guess. No.
Yes.
Yeah, but my doubts about this equation of states is always that this measure, I guess, nuclear densities, while what you show.
No, actually, this PREX experiment that measures the neutron skin thickness.
Okay.
And from that, these two quantities can be determined.
Okay.
Yes.
Yeah, because you show that you get supernuclear densities, like 2-3 times typical nuclear densities.
Yes.
So this, I guess, requires some kind of extrapolation, right, towards
yeah.
from data you can collect in experiments towards something that is quite more extreme.
Yeah.
Okay. If not more questions, we move on. Thank you.
Vale. Okay. Hi, I'm Silvia. I'm a PhD student at IFAE, and now I'm going to talk about pinning down the properties of black hole mergers with gravitational wave memory. So first of all, I want to introduce what a gravitational wave memory is, because it's a very interesting topic, and it's a result of the nonlinear nature of gravity. Theoretically, it was discovered about 8 years after the first paper on gravitational waves by Einstein, and in a sentence, the gravitational wave memory is the back reaction of the gravitational field on the emission process of gravitational waves. We can understand it from equation here. So we know that from Einstein equation, we can linearize them and end up with this equation. This is a wave equation for the space-time perturbation. And on the right-hand side, we have what sources the perturbation. And one normally focuses on the energy momentum tensor of the matter that is on the region of space that we are interested in. But we know that, well, general relativity tells us that any form or energy modifies space-time. So we have to consider also, we should consider also the energy momentum tensor of the gravitational wave itself. And including this effect is what is called the nonlinear gravitational wave memory. So we know that it's a small effect because it's a effect of second order in perturbation theory, but it turns out that it can modify substantially our signal. And this is well, this is the contribution of the memory that we see for a massive binaries merger. So what we see is that the 0 point of the oscillation increases with time, with a, well, most of the accumulation is during the merger phase. And at the end, we end up with a finite offset of the 0 point of the oscillation compared to the beginning. And this is what is known as the memory. Okay, how do we compute it? Well, from the wave equation that I showed you before, you can use the standard technique of the Green function, and this is the final formula for the memory. And here I just want to highlight a few things. So the value of the memory at every moment in time, it depends on the whole history of the system, because you have to integrate it from minus infinity. And this is the reason why this effect becomes important, and it modifies our waveform at the 0 post-Newtonian level. Then another thing is that as long as the energy flux of the gravitational wave is non-zero, we have a non-zero delta H. And well, the effect of this non-zero delta H is that it leaves a permanent distortion of the relative position of test particles. So we can see this effect from this figure here. Basically, we start from a configuration of test particles, and the relative position gets modified as the wave passes through it. And then in the absence of memory, we end up like with the same configuration at the beginning, but this is the residual effect of memory. And as I said before, this contribution enters at the 0 post-Newtonian level of the waveform. So this is what I'm showing here for just the plus polarization. So this first piece is the oscillatory component that comes just from the quadruple formula, whereas the second term is the contribution from the memory. And we can see already that, well, this is suppressed compared to the first term by at least a factor of 20, and it has a different angular dependence on the inclination angle. Then, and it's not oscillatory, this is also important. And then both terms multiply the same amplitude factor that it depends on the total mass, on the mass ratio, and on the orbital frequency. And what you see here is that basically, the time dependence of the memory traces well the evolution of the orbital frequency, that it looks like a step function with a steep increase at the merger, during merger. So this fact tells a lot about the shape of the signal in frequency domain, because the Fourier transform of a step function goes like 1 over f. So this extends the signal at arbitrary low frequency. And so this is the theory. And what we have investigated is, can the memory help in parameter estimation for the parameters of our binary? And mainly, I focus on if the memory can help in breaking the degeneracy between the inclination angle and the luminosity distance. And okay, so I did some forecasts for LISA, that is a space-based telescope that is going to measure merger of supermassive black holes, and I did a Fisher analysis. And what you can see here is that indeed the information coming from the memory is kind of orthogonal to the information of the main signal, but it turns out that being a small effect, it can help only in a few cases. So mainly, the memory helps for light signal and short signals. Light, because for these binaries, the merger occurs like on the less sensitive part of the detector at high frequency here. And so the memory that extends the signal at lower frequency covers the most sensitive part of the detector. And then light, well, short signals, because as we keep looking a binary, the uncertainty on the parameter shrinks down, and the importance of the memory becomes, well, decreases. And indeed, here you can see the relative improvement of including the memory as a function of the number of cycles of the main signal. So then we asked, okay, if we take some astrophysical models of supermassive black holes, how many events are we going to see with how many events can we observe the memory? And what we found is that the number really depends on the astrophysical model, but in general we expect more than a few events with memory with an SNR greater than 1. And here you can see, I mean, the average improvement on the luminosity distance by including the effect.
Questions?
Hi, very interesting. Maybe it's a stupid question, but what about neutron star mergers? In this case, you would have you go in the limit of low masses where your signal seems to be more relevant. So would, in the case of neutron star mergers, be much more important what you're doing, or is that not the case?
Thank you for the question. And this is, yeah, you understood the real point, that the memory helps as it extends the signal at lower frequency. It mainly helps when the merger occurs like a kind of out of band. So in the case of neutron stars, if the binary is light enough that you don't see the merger, yes, of course, the memory would help a lot. But the point is that as you consider lighter masses, then also the signal of the memory becomes fainter. So it's difficult to tell if what you are seeing is actually in the memory coming from the merger if you don't see the merger in the first place. Yeah, this is a bit tricky. But yeah, there are studies that even consider the memory for disentangle different equation of states for neutron stars. Yeah.
Okay. Thank you very much, Silvia.
Okay. Can you hear me? Okay. Thank you for the opportunity to speak today. Today's presentation is collaborating with Osamu Seto. So if you think I'm interested in my presentations, please also read these papers. The cosmological standard model, lambda CDM model, has been successful, explaining the evolutions of our universe. However, the tensions of the Hubble constant between the distant observations and local observations has appeared. In the distant observations, assuming lambda CDM model, Hubble constant is derived around 67 km/s per megaparsec. On the other hand, in the local observations, the Hubble constant is measured around 73 km/s per megaparsec. And these tensions exceeds 4 sigmas and recognized as the serious problems. And we called the Hubble tensions. To solve the Hubble tensions, several ideas have been proposed. Among such ideas, today I'd like to focus on the varying electron mass models. In the varying electron mass model, we use the fewer additional parameters, but we can give the large improvement in total delta chi-squares. So the the varying electron mass model is one of the most promising solutions to the haploid issues. Okay, and in my presentations, I'd like to consider the varying electron mass model and its consistency with the Big Bang nuclear surfaces. And through the considerations, I'd like to summarize that the varying electron mass model is limited by helium abundance measurements. So immediately, I'd like to discuss about the varying electron mass models. Today, I'd like to consider the case that the electron mass at CMB or BMN is greater than today's. For examples, the electron mass at the BBN and CMB is a few % greater than today, and after the CMB errors, the electron mass drops to the today's values. So next, I'd like to discuss about the effects on CMBs. In the case that electron mass at last scattering was greater than today, namely the electron mass at last scattering over electron mass at today is larger than 1, the photon loses energy earlier to excite electrons in hydrogens because the energy level of hydrogens is proportional to the electron mass. And then the recombinations occurs earlier and last scattering time T star gets shorter. However, we cannot directly measure the value of the T star, but we can measure the anisotropies of the CMBs. Therefore, this anisotropies includes the informations of the angular size theta star equal r star over dm stars. The r star is the comoving sound horizon at the recombinations, and dm star is the comoving angular diameter distance. The Planck satellites directly and strictly measured the value of the theta star equal 1.041 times 10 to minus 2. After the calculations, you can find that the strictly valued or theta star is proportional to the Hubble constant times r stars. Therefore, when the electron mass was greater than today and last scattering time the star gets shorter, the horizon scale r star decreases and Hubble constant increases. This is the result of our Markov chain Monte Carlo analysis using the data, the CMB from Planck, the baryon acoustic oscillations, and the local measurements of the Hubble constant from shoes. You can find that greater electron mass leads to the higher Hubble constant. The yellow band is the limit from the local measurement of the shoes. So you can also find that the few % greater electron mass leads to the few % greater electron mass reveals the Hubble issues. And the electron mass model, varying electron mass model, is a promising solution to the Hubble issues. However, another concern is Big Bang nuclear synthesis consistencies. So next, I'd like to discuss about the Big Bang nuclear synthesis. In the case, the electron mass at Big Bang nuclear synthesis was larger than today, namely ME at BBN over ME at today is greater than 1. The neutron lifetime gets longer, neutron to proton ratio increases, and helium mass fractions YP also increases. Therefore, the result of our analysis shows that the greater electron mass leads to the larger helium abundance, and also the great Hubble constant leads to the larger helium abundance. The x-axis shows the electron mass and Hubble constant, and y-axis shows the helium abundance. The orange band is the limit from the helium measurement. So you can also find that there is great discrepancies between the higher Hubble constant and helium measurements, or greater electron mass and helium measurements. So as a result, the blue contour, which includes the BBN data, this favor the greater electron mass and higher Hubble constant than the red contour, which is without the BBN data. We use the data BBN as the helium and deuterium. Therefore, the greater electron mass is disfavored from the helium measurements. So this is the take-home message. Thank you for your kind attention.
Questions? We have two. We can do three. Let's.
My question is short. So, okay, I didn't know about this, and it's very interesting. But I have a question. So, is there any theoretical reason why the electron mass should change?
The most popular model is the coupling between the Higgs and axions. And another model is like the brane world theories, which couples Dirac mass and the bulk scalar fields. Is it okay?
Okay, maybe follow-ups.
Very quickly then, so in this series, I assume there is going to be a mass redshift dependence of the mass evolution, because today there is no hint for deviation. So have you tried to see what kind of redshift dependence might fit the bill of the CMB and BBA at the same time? Like you could have some peaks or suppressions or something like this? Like the new physics appearing on some scales that avoid the BBN constraints?
Sorry, question again?
Yeah. So if you base yourself on actual models, I assume the the redshift evolution of the mass is not going to be constant over all scales. Also because today there is no deviation of m. So I was wondering whether some models suggest some more complicated redshift dependence that might, for instance, evade the BBN constraints.
Yes, of course. We should include such an effect.
Okay, let's thank Giotto again for his talk, and let's go towards the last one by Luca Teodori.
Okay. Hi all, I'm Luca from Weizmann Institute, and today I will talk about the machine degeneracy in cosmography analysis. Whoa! Stop the watch, please. Okay. Unfortunately, I think fear spoiled a little of what I'm going to talk about, but maybe this is good because then I can be fast in certain things. So again, the Hubble constant tension, again, we already talked about it, but in short, we have a tension between like the late time measurement of the Hubble constant, the early time measurement of the Hubble constant from CMB and distance ladder, pi sigma tension measurement, and strong gravitational lensing gives us a new way to measure the Hubble constant independently from the other. And it's interesting to see where this measurement sits because it can reinforce or otherwise the Hubble tension. And from an early result from the TD Cosmo collaboration, we see that in the beginning, it seems the measurement seems to reinforce the Hubble tension since it sits together with the supernova 1A Cepheids measurement. However, when it takes into account some degeneracy in an upcoming paper, we see that the error bars of the measurement shrunk a lot, and hence, as of now, the strong gravitational measurement cannot say whether we cannot say where it sits. This comes from a well-known degeneracy called the mass sheet degeneracy, and where there are two sides of it. One is the external one, and one is the internal one. I will try to discuss a little of these features, and hopefully at the end give also an insight of what multiple source systems can give us. So here I can go very fast. What is strong gravitational lensing? Basically, we have a source in the background, typically a quasar in this kind of measurements, which whose light path gets deflected by means of a intervening mass, usually in this kind of analysis, a massive elliptical galaxy or a cluster of galaxy. And hence we see like the image of the source in a different position with respect to its original position, which we call beta. I remind that this original position, which is called beta here, is unobservable. We cannot observe it. Okay. And in general, how can we obtain the Hubble constant from this setting? From a lens model, from trying to fit a lens model from the image we see in the sky, we can find good parameters for what this lens might be, and then with the measurement of the time delays, where here I show like a picture of time delays of light curves coming from 4A image system. From a measurement of these time delays, we can combining with this lens model we find from the reconstruction problem of the imaging, we can infer what is the Hubble constant. However, again, unfortunately, there's this degeneracy called the Machite degeneracy, which basically tells us that if we change our minds about what is the actual position of the source, which again is unobservable, and also about the model, we just rescale the original model with this factor lambda, plus we obtain this term that might be physically interpreted as a sheet. Then we basically change the inference of the Hubble constant, and most notably, this change, this Machite degeneracy, doesn't change anything about the imaging part. Like the image that we see remains the same under this transformation. Now, there are two types of Machite degeneracy. One comes from the large-scale structures, one might come from the internal, it might be internal to the lens. From the large-scale structures, one can show that when you solve the lensing equation, since the picture is a little different with respect to what I showed before, there's not just the main lens that causes the deflection, but there are all the intervening matter from source to lens and from lens to observer. This effect, if they can be somehow approximated as a first order approximation, they can be decomposed in three key quantities relevant for the Hubble constant measurement. There are other quantities, but now for lack of time, I'm not discussing them, which is basically the so-called convergence between observer and source, and the convergence between observer and lens, and the convergence between lens and source. I must remark that these are independent variables. In general, in TD Cosmo analysis, what they try to infer somehow, I don't have time how they do it, but they try to get a prior on this kappa S, this convergence between observer and source, but they kind of ignore, for some reason, actually I don't know why, these two terms that unfortunately enter into the determination of the Hubble constant with one takes time to check it. In particular, we remark from the fact that if you don't take into account the presence of this convergence, when you try to constrain your machine degeneracy from stellar kinematics can do it because thanks to stellar kinematics, you can have a prior on the mass of what your lens system is. And if you recall here, when I do this machine degeneracy, I rescale the original model, meaning I change my mind of what the real mass is. Well, but if you don't take into account the effect of this weak lensing, you have a bias in your measurement. In particular, one can show that you have a bias between the inferred H0, where you just ignore these terms, with respect to the true, that goes like this. And this is like most likely 2-3% effect. It's not big, but if one wants to claim that want to reach a 1% precision of the Hubble constant, has to take into account, and as of now, it's not taken into account. Another thing from machine degeneracy come from the internal one, which come as Kfir said, from large unaccounted core components. In particular, I wrote with him with this paper about the possibility that ultralight dark matter can do the job. But I want to stress the fact that the main message that we want to convey here is not that ultralight dark matter is there and solves the Hubble tension, because it doesn't matter if it's ultralight dark matter, self-interactive dark matter, dragon dark matter, really doesn't matter. What matters is that this modification of the assumption of just a simple Navarro-Frank-White profile, which is most likely to break when you have small scales, can have effects on this Hubble constant. A last comment about the possibility that multiple source systems can help us in try to understand a little more this issue. It's interesting because something I didn't say is that these three-factor called external convergences are unobservables, meaning they can be reabsorbed in your model parameters. However, when you have multiple sources, you can absorb only one external convergence coming from one source, meaning that the differential external convergences factors become observable, which this is pretty remarkable. I think almost nobody really focused the attention of this. You can really probe something that seemed to be really unobservable. Unfortunately here, if you think that internal machine degeneracy is there, you have that you're observable as, yes, differential external convergences, but that as also a term that comes from external differential internal convergence, okay? But this can be still a good sign, because if it just so happens that lensing collaboration measures this object, delta kappa ops, and then it just finds that it's way too large to be just explained by this differential external convergence from a possible cosmological view, then it might hint at the fact that there's indeed some mismodeling of the main lens. So this possibility, and I remark right now, multiple source lens systems are just a handful, but we expect to have many more in the future, especially with LST. And thanks to this, we can try or to spot the core or to characterize better the line of sight. So I leave you with the conclusion. I will just remark at this point that studying this degeneracy coming from the Hubble constant tension is interesting regardless of the tension itself, because let's say that in the future we have like a good measurement, the Hubble tension is not anymore there, then what I just showed means that the degeneracy is not there, meaning we are sensitive to interesting properties of the lens galaxy that cannot be probed otherwise, or we can characterize better the line of sight. Thanks.
So, questions? Anybody?
Thanks for the talk. Maybe the collaboration is already doing this, but to get more multiple source messages, do you use multiple different wavelengths as well? So for example, optical lens sources, but then also radio?
I mean, gravitational lensing is not sensitive to the wavelength of your object. Like gravity doesn't care about the wavelength. Like plasma effects might care, but they are too weak with respect to gravity as far as I know. So.
Yeah, no, I meant more in the sense that maybe you have a strong lens that has a galaxy in the optical that is lens, but then also a different object, different source in radio.
There are certain studies that try to understand the potential of lensed fast radio burst, for example. And there it's not about the frequency, but it's about the impulse. Like you have like very fast impulse, and thanks to this very fast impulse, you can superimpose your image and have a very, very precise measurement of time delays. This is a possibility. Repeated fast radio bursts are there. We saw it, but still we didn't see any lensed repeated fast radio bursts. But it's indeed a possibility with the new surveys, LLST and whatnot. It might be. It's discussed in the literature. Yes.
Okay, thank you again, Luca. Thank you to all the all the students who gave talks, and also to the lecturers who attended the session. And yeah, we will see each other tomorrow in the morning.